Now, because it's our first time talking about a single organ system, I kind of want y'all to think about how to do this well, okay? One of the first things that we need to do whenever we are trying to kind of get ourselves oriented about a topic is think about what we already know, okay? So with that being said, move this over here. All right, so what do we already know about the skin? Our integument. What does it do? What's it for? All right, so it's for protection. Protection from what? Outside world, okay? But what's outside that we need to worry about? So diseases, infections. What else? That's it. That's all that's in the outside world we have to worry about are diseases and infections. That's still, I would say that falls under diseases and infections. Like you can get fungal infections, you can get bacterial infections, you can get viral infections. What else? Insects, right? Okay, so we have to worry about things like insect bites and stuff like that. Okay. All right, so those are all different ways of protect. But all right, what happens if you take a cell and you put it in a fluid that has a higher concentration of water than what is inside the cell? What happens to the cell? It bursts, right? Because water goes from the outside environment to the inside environment, right? And those cells can break. So we also have to protect from water. Right? We have to protect ourselves from water that comes from outside and like getting inside of our cells. We also have to protect ourselves from the opposite direction. We live in Texas where it gets hot as hell outside sometimes, and where we will sometimes go many days without seeing water, right? So what do we also have to protect against? We have water in our cells, exactly. So we have to protect against dehydration. What does it usually look outside when we are protecting ourselves against dehydration? What does it look outside usually? Like, what does it look like outside when we are protecting ourselves against dehydration? It's hot, so what's it look like? When it's hot, what do we need? What is making it hot? The sun. Yeah, we have to protect ourselves from the sun, right? This list could go even further. Okay. What's something else that we do with our skin other than protection from all of these things? So what's something else our skin needs to do? Anything else? Do we use our skin for anything else? It's just a protective barrier, that's all. Absorption. Absorption to a small degree of some stuff. We could say secretion of other things. So absorption, secretion. Okay, that's a minor role, but it's definitely there. We can absorb things through our skin. We can secrete things out of our skin. Okay, what else? If something lands on you, do you know it? I would hope so. If a spider is on me, I want to know, and I want to know now. That way I can die of a heart attack. Okay, because that's what would happen if there's a spider on me. You don't believe me? I was actually fishing at like a little pond behind my house that I'm technically not supposed to be fishing, I don't think, because I don't own it or know who does. But anyway, was trying to land a fish at one point, and I bent down and I saw that my face was about yay far away from one of those what do people call them out here? Like garden spiders, banana spiders, those yellow and black and white ones that put those big webs out like this. I was literally this close to one. I looked at the eyes, squealed like a little girl. Okay, not a joke. And I literally like ran with my fish like this way, away from it, because I thought I was going to be in it. Okay, we want to know if something is touching us. So we need sensation, right? Okay. Now, this is not an exhaustive list yet, okay? Over time, we will make this more exhaustive. But this is kind of what your brain does whenever you bring up a topic. When you think of the skin, your brain is immediately going to jump to all these things, okay? Like, that's what I've had you all doing, is just trying to recall some of the stuff that your brain is thinking about when it thinks about your skin. So what we're going to do is basically, as we were learning about stuff, we're going to go through and we're going to say, like, okay, what are we doing to prevent dehydration? And we could come out here, and now we can kind of open up our mind map a little bit and say, like, oh, we're doing this to help prevent dehydration, or we're doing this to protect ourselves from water. We're doing this to protect ourselves against these things, right? So we can expand this map out so we have a better understanding of what's going on, okay? But all of this is right. We absolutely need absorption and secretion in our skin. That's a very important function. We absolutely use our skin for lots of protection in lots of different ways. So we have to protect ourselves from different things. And the way we do that with our skin is going to be a little different depending on which thing we're talking about. Same thing goes for sensation. What do you think we need for sensation? Something else that we already know or might already know. What do we use for to sense sensation? Our nerves, right? We know that we have to have some sort of nerves here, right? So we can continue kind of opening this thing up, and hopefully by the end of this class, our little mind maps of each one of these topics is going to be a lot larger than it was when we started, with a little bit more depth in some of these ends, okay? Now, importantly, our skin is, of course, going to be that covering, okay? It is what's going to separate our inside world from the outside world. So we do have to protect against lots of things. Now, importantly, it is not just going to be our skin that is doing this. We've got several other structures that are helping us here. We have our nails, our hair, and then we also have glands, our sweat glands and our sebaceous glands, okay? I said sweat glands up here. I'm surprised no one mentioned temperature regulation. We sweat, do we not? When it is hot. Our skin also tends to get a little pale when it gets a little cold. Why? Because we want less blood getting close to that skin and losing heat that way, okay? So as we move through, we're going to kind of add some stuff to our little mind map here as we're moving forward. I also really recommend that you kind of do this stuff for yourselves at the start of every chapter too. Always think about what you already know, and then we can kind of expand that. We're going to fill in some gaps. There's some spaces here, things that we don't know, so we can put extra lines off of here, but we can also expand on the stuff that we do know, okay? Now, importantly here, we are also looking at a visual indicator of our physiology and health. We can see and recognize lots of different things that are happening in someone's body based off of some of the stuff that we can see in our skin. If you have vitamin deficiencies, you'll see that as like little pits and gouges in your fingernails. If someone has jaundice, okay, you're going to see that as their skin turning yellow. If someone is, say, standing in this room, it's like what, 68 degrees, maybe 70? It's relatively chilly, and that's coming from me, okay? Which means you back there are probably, yeah, not having a good day. Well, if I were standing up here doing virtually nothing, and I was red in the face and sweating and stuff like that, even though it's 65 degrees in here, that would tell you that there's likely some sort of problem happening, right? So we can use that as kind of a clue as to kind of what's happening in our bodies in a lot of cases. And this is especially helpful since we can see these things, because it is, well, the outside barrier. That's what we get to look at when we look at somebody else. Like, I can't look at your innermost, like, deepest, darkest feelings and fears and stuff like that, but I can see the surface of your skin, right? So we at least have some sort of indicators in some cases. Now, our skin is composed of 3 layers, or our integumentary system is composed of 3 layers. We have the epidermis, the dermis, and then finally the hypodermis, or the subcutaneous layer, okay? Technically, the subcutaneous layer is not part of the integumentary system, okay? It is basically just going to be a layer of tissue that's going to connect the integumentary system to whatever stuff is underneath it, whether it's muscles or bone or whatever that may be, okay? Now, the epidermis is going to be this set of structures up here. It's this outermost layer. So the outermost layer of our skin is our epidermis. Epi meaning outside. You should get used to seeing epi meaning the outermost layer of something, okay? Now, the epidermis is composed of, actually, let's see if we can figure that out. All right, looking at this, we see a bunch of kind of fried egg looking cells, right? So what kind of tissue is this? It's multiple layers of these fried egg shaped cells. So what kind of tissue do you think this is? Stratified, perfect. Perfect. Stratified squamous epithelium. It is composed of the epidermis is our outer layer. And it is stratified squamous epithelium. What do you think that we are getting? What functions are we gaining by the fact that we are made out of stratified squamous epithelium? So what does squamous epithelium look like? So what does squamous cells look like? Little fried eggs. So they are flat and they are thin. Now, I drew this cell with a nucleus, the yolk of our egg. Do you see yolks in our eggs up here? No. So these cells don't have a nucleus. So now, instead of our fried eggs having the best part of the fried egg, our cells don't even have nuclei anymore. They're just a bunch of measured out bits of egg white. So what function could we possibly be gaining at this point? What could you do really easily with something this shape? Stack it. Things that are big and thick and heavy might be kind of hard to stack. These are not. So because they are super thin, we get these big interlocking stacks of cells where we can have adhesion between not just this cell and this cell, we also get to adhere this cell to this cell and this one to this one, which means we get to make something incredibly, incredibly strong. Just like the shingles on your house. Having a single layer of shingles on your house doesn't do a whole lot. If you just put a single layer of shingles on a house, it would actually stop some water, but not that much. You'd have to replace the entire roof fairly quickly and all the boards and stuff underneath it. That wouldn't be great. But simply by adding 1 or 2 layers like they do, all of a sudden that becomes a once every 30-year job. All because the additional layers generates that much extra strength, and it also generates that much extra distance through which something like our insects or our bacteria, viruses, fungi have to go through. They might be able to get down to here, but it's so thick that it's really difficult for them to get down here where it actually matters, right? Now, we also get something else by using stratified squamous epithelium. Do you see blood vessels moving through our stratified squamous epithelium? No, which means those same bacteria, in order to get to anything that could actually hurt us, have to get to the blood before it can do anything to affect the system as a whole, which means it is a long way away from being able to hurt us. Does that make sense? So we get this massive, thick protective barrier because of our stratified squamous epithelium. It helps us with protection simply because we have this big, thick layer of cells. A thick layer of cells. That thickness is where we're getting our protection. Okay? Now, these cells are also going to be filled with a protein called keratin. Okay? Keratin is very, very tough. It's the same stuff that's in your fingernails and your hair. Okay? That stuff is really, really dense, really, really thick, really, really strong. That is one of the other ways that these cells are going to help be like these shingles on your house, is because they're going to be filled with this protein. So that's more layers means more of that protein, which means even more protection. Now, We're also going to find a couple of sensory nerve receptors that are going to move up into the epidermis just a little bit. In fact, I actually don't even see a single one of them on this particular figure. Okay. We will have some nerve endings that will go up into the epidermis, but not very much. Most of them are going to be found down here in the dermis. Okay. Now, I want you to pinch your skin and pull on it. So kind of pinch yourself a little bit and pull. Can you separate your epidermis from your dermis? No, it's quite hard. You have to pinch yourself incredibly hard and pull really, 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 really hard to separate your epidermis from your dermis. When that happens, that's called a blister. Okay, that's what's happened when you get a blister, is that you have separated your dermis from your epidermis. It's not very common. It doesn't happen all the time. Okay, it sucks when it does, but it doesn't happen very often. Okay, that's part of why it sucks so much. Is like, man, this is really rare. This is awful. Okay. What you've done in that case is you've separated your dermis from your epidermis. So what we need then is something that's going to tie these two things together. Okay, so if we have our dermis, which contains most of the structures of our skin, or complicated structures of our skin, it is going to be below our epidermis. So we have to have something that's going to connect them. The region that's going to connect our epidermis to our dermis is called the papillary region, or papilla. So the papillary region of our dermis, or our epidermal papillary ridges. Okay, they're basically the same thing. They're just in opposite directions. The epidermal ridges point down towards the dermis. The papillary region of the dermis points upwards towards the epidermis. So you basically get these big finger-like projections of epidermis and dermis interlocking together. So what do you think we're getting by having all of these big finger-like projections interlocking themselves? What are we gaining? We're gaining lots and lots and lots of adhesion points between our epidermis and our dermis. We are getting more surface area. Every time I have said that you see ridges or like big wavy lines or something like that, that you think about surface area, we have these in this case, so we get more surface area. More surface area means we have a stronger connection between our epidermis and our dermis. Now, here is a question. Do you expect to see larger ridges or smaller ridges in our hands versus, say, our arms? Which of those do you think is going to have larger epidermal ridges? The skin on the palms of our hands or the skins on places like your forearms? Where do you think we're going to need more strength? Our hands. Why? Because we use them more. That's exactly right. Don't you put a question mark there. That's correct. Okay. You touch more things with the palms of your hands and with more force than you do something with your forearms. Like, when was the last time you picked up an object using your forearms and actually subjected your forearms to massive amounts of friction? Probably not very often, to the point where what I'm doing right now looks ridiculous. Right? No. Instead, wait, what screen am I sharing? Okay, it is the right screen. It just looks funny on my computer. To the point where, like I said, that looks ridiculous. No, we touch things with our hand. If I wanted to pick this up, I'm going to use my hand to do that, which means I am subjecting my palm to the friction that's required to hold on to this. Okay, so the ridges in my palm are going to be larger, and say the tips of my fingers are going to be larger than on my arm. So this model is showing us the difference between two different types of skin. We have thin skin on this side, and we have thick skin over here. Thick skin, like found on the palms of your hands and the soles of our feet, do not have hairs, at least last time I checked. Nope. Okay, so we don't have hair on the palms of our hands or the soles of our feet. We don't have the glands associated with those, so we don't have sebaceous glands or anything like that. But also, the skin is much thicker. Why? Because it's subject to a lot more friction. But also, the ridges that connect our epidermis to our dermis are much, much more pronounced in our thick skin. Do you have fingerprints on your arm? No. At least I hope not. That would be weird. Right? But look at your fingertips. Look at the palms of your hands. You see those ridges? Those are called friction ridges. They are friction ridges because, if I can make the sound. Oh, it's so slick, I can't. Okay. That sound is because my fingers are putting friction on the surface of that smooth board. Those little tiny fingerprints, or those little tiny ridges, are actually caused by those dermal papillae in between the epidermis and the dermis. In your hands, they line up in these nice little lines. Instead of being evenly distributed, they line up in these little lines so that you get these big bumps, these big epidermal ridges or friction ridges on the surface of your skin, your fingerprints, so that you have more surface area for more friction. Okay? I am not particularly strong, but I can hold like 50% more than my body weight just by grabbing something with my fingers. Just and I can just hold it. Okay? There are professional climbers that could take something like this, held sideways, and grab it with one hand and hold themselves up. Which is basically them applying force through their fingertips and through those friction ridges. They get enough friction between their finger ridges and the surface to support their body weight on a hand. It's impressive. It also pisses me off because they make it look easy when it's not. Climbing is especially one of those sports where it's like when you are at 98% of what it is you're doing, you can still make it look like, oh, this is completely fine and it doesn't actually seem all that hard until you just fall off. Like that last little bit, like doesn't look like anything particularly special. You just fall just because like, oh, I don't have enough friction anymore. Geckos have specialized extensions of the epidermis on their skin to where they get thousands of times more friction than you and I can get so that they can actually climb upside down on glass. You could literally take a pane of glass and not all geckos, but some geckos, you could literally take them and stick them to that, or like let them grab onto that glass and they could just climb on it. On glass, upside down, because of the extensions of their friction ridges. It's super fun. I'll show y'all a picture of that when y'all are studying here a little bit because they're super cute too. The Geico gecko is actually one of the ones that can do that. He's called a Madagascar day gecko. So they live in Madagascar, but they're one of the ones that have these super crazy, like feather-like ridges on their fingers. Most geckos do. Even like the little Mediterranean ones that we have like around our houses. Like if you've seen those little tan lizards, like with the black and brown spots and like the little white and black striped tails, like around your lights and stuff like that at your house. Yeah, like one of the little babies. They probably died. Most babies in the world die. That's just how it works. Like most animal babies die. But they can do that. If you look at them real close, you can see these little lines on their fingers. And that's what they use to stick to stuff. And it's just basically these same things just kind of blown up to a ridiculous degree. Now, that is in our epidermis. We're going to talk a lot more about the layers and stuff there here in just a second. But then we have our dermis down here. We still have that papillary layer where we're going to find lots and lots of blood vessels. Because epidermis doesn't have blood vessels. We have to supply these cells with blood. They're going to get that blood from the dermis. I mean, the dermis is the area of your skin that has lots and lots and lots of blood. That's why you can actually take your skin and just kind of scratch it. And I don't see blood pouring out of my arm, even though I am scratching hard enough that y'all can probably hear it, right? Okay, yet I'm not bleeding. Why? Because, well, there's a bunch of stuff in the way. There are no blood vessels up in that stuff that I can get to really, really easy. Ooh, that got hot. But there's no blood vessels in that surface area, in part for protection, but also in part because we still need to feed those cells with stuff. So those blood vessels have to be somewhat close, okay? And they're going to be coming through these papillary regions. They're just going to pass through those papillary regions so we get them close. Now, because we have no blood vessels here, though, and our blood vessels are down here, that's actually why we see this demarcation line in our epidermis of the living cells, which are these pink ones, and our non-living cells, which are these kind of brown ones up here, okay? Part of our epidermis, or a big section of it's going to be composed of non-living cells, okay? Why? Because we got too far away from the blood supply. If we get too far away from the blood supply, the cells are going to die. They're not getting enough oxygen. They're not getting enough sugar. They're not getting enough proteins. They're not getting enough of any of those things. So, or some of those things. That means they will die. However, we're just going to have them all tacked together. So now we basically have shingles on the outside of our skin. And if some of those get sloughed off because we're a jerk and we scratch at our skin, it doesn't really matter. Okay? Because we have a bunch of them underneath. Like you can scratch off 5 or 10 layers right here. It doesn't really matter. Why? Because there's more cells underneath. Okay? But that's also why if I have gone, like I've done here, and scraped away several of those layers, notice that my skin's turning pink. Why is my skin turning a little pink? Because I'm irritating it. That is part of it. But also because I'm scraping away some of the invisible dead cells that we can't see that are actually stopping our ability to see the blood and stuff underneath. Okay, so I've scraped enough of these things away that now we can see some of the pink living cells down here. And then, yes, these pink living cells are now angry at me, so they're kind of filling up with fluid and stuff, so they're making themselves even larger so that we can see them even more. They are irritated. Now, also found in the dermis is where we're going to get lots and lots of fun, complicated looking things like we have sebaceous glands and hairs and blood vessels and various different types of nerve endings, whether it's nerve endings up here in the papillary region, which are very sensitive, or nerve endings down here towards the hypodermis or kind of in the middle that are going to be less sensitive or sense things like stretch in the skin or deep pressure. So notice that we have some up here, some down here. The ones up here are going to sense light touch so that you know if just something is touching the nice surface of your skin. Okay. These down here are going to sense low frequency vibration and deep pressure. So your ability to distinguish between being grabbed versus something just lightly touching your skin is going to come from the different sensations coming from these two or the different types of nerve endings found in these areas. Okay. Now, then we have our hypodermal region or our hypo-Q or subcutaneous region. Okay. This is a layer that's going to be composed of areolar connective tissue, which is going to be these kinds of regions here, which remember contains lots of collagen, lots of elastin, so it's quite strong. Also quite stretchy, but it's also going to contain a lot of adipose tissue. Okay. So in order to get to the adipose tissue, so if you've ever had a cut that's deep enough that it gets down to the fat, okay, that tells you that you've gone not just through the epidermis into the dermis, but that you've gone deep to the epidermis and actually gotten into the fat. Okay. So in order to actually cut someone so deep that you can see the fat beneath, that means you have had to go through all of this structure here, which is quite difficult to do most of the time. I bet you can probably only think of 1 or 2 times in your lifetime that you've been cut so deep that you can see the fat underneath. Okay, if that many at all. Okay, if you can't think of any at all, that means you're fairly lucky and haven't actually hurt yourself all that bad. But I can think of a few times that I've been able to do this. Each of them involved stitches and or staples. Super fun. See, here, 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 here. I think that's most of them. Huh? What did you do? Rock from falling off a bike, rock from falling off another bike. Wait, hold on. No. Rock from falling off a bike, rock from falling off a bike. This one was falling off a bike off of a roof. This one was I was running through my, like, I had some of those like exposed bookshelves, like basically like a slat of wood coming off the wall. And I like tilted too much. So, like I leaned into the turn as I was running into my room and clipped it. You could see my skull on this one and this one. It was bad. Like the person that was like stapling it closed, particularly on this one back here, like asked my mom if she wanted to come see my skull because it was all the way down. This one was also came with a concussion. It was fun. But like a stuck pig. I couldn't like literally like a sheet of blood coming right down here. This one was a bowl, like through a trash bag, just sliced straight through it, like all the way down into the fat. It was great. What, y'all haven't seen your fat underneath your skin? You're not trying very hard. And those are just the things I could see. So many bruises, it's ridiculous. I'm very clumsy. I've also dislocated both shoulders. No, that's the whole point. Like, you have to try yourself, man. When we took our kid, I think it was like third or fourth year checkup. We took my son to like see the doctor, and he just had bruises all down his legs, like a couple scratches and stuff like that, like where he'd gotten into something. He was like, "This is what I like to see. This is a kid that's actually out like doing stuff." Like, no, he shouldn't be like pristine, like bruises and scratches and like no, that just means he's actually like trying his strength. Like we need to be doing that kind of stuff. We need some exposure. Like it wasn't like bruise like we were hurting him. It was true. Just like, oh, he like ran and fell, or he ran into something. Like he'll be okay. Do more things, man. So we're going to talk about some of these structures and these various things now. All right, now epidermis, outermost layer, is composed of 5 different layers of cells. Okay, or 5 distinct layers. Okay, all of these are going to be filled with primarily keratinized keratinized squamous epithelial cells. Okay, this means that they are cells that are filled with a protein called keratin. Now, from deep to superficial, so as we are starting deep, that means closer to the inside of the body, right? We are starting with the basal layer. Okay, so the basal layer, or the stratum basale, is going to be composed of these squamous epithelial cells. However, these are going to look more cuboidal. They're not going to be our fried egg cell shape yet. Okay, they're going to mostly be made out of these cuboidal cells. Okay, now we will have a couple of other cells that we're going to find in this area. Try to get to a picture. There we go. So here we have our basal layer here. We have our keratinocytes, but then we've got 2 others. We see this one right here. The cells, it's kind of coating in brown here, and it's got these little fingers kind of reaching out in multiple directions. If you could blow these fingers up, you'd see they're going to be filled with dark granules. The dark granules are melanin. Okay? Melanin in our skin is going to protect our cellular nuclei, so protect the nuclei of our cell with the protein melanin. Now, melanin basically is going to act like a shield. So if this were one of your cells, so say we have our fried egg cell here. Here we have our nucleus, very thin, a little bit of layer here. All right, so there's our cell. If we have our nucleus here, what we're going to do then is with melanin, we'll basically make like a little shield with this protein, with these little protein granules around the outside of our nucleus. Why? That's because the sun is up here, right? The sun's not coming from down here. The sun is up here. That means that's where we need the shield, okay? So we're just going to use that melanin to keep the UV radiation away from the nuclei of our cells, okay? That melanin is produced by the melanocytes, which are, like I said, these little cells here that have these little kind of dendritic regions kind of reaching out, these little finger-like regions reaching out around here. Okay, so those are going to release the granules that can then make their way into the neighboring cells, and then that melanin can act as a shield. Now, something fun happens with melanin, and that is that its levels are going to be determined by a couple of things. One is genetics, okay? There's going to be a different amount of melanin that each of us is going to produce simply based off of our genetic background, okay? There are also different types of melanins that can be produced. We have eumelanins, and there are more than one, where some of these are going to be black in color, some of these are going to be brownish in color, okay? If you produce more of the darker ones, you're going to have darker skin. We also have pheomelanins. These are going to produce things like yellow and tan and red, okay? If you produce more of the red ones or more of the yellow ones, your skins are going to take on that kind of hue, and just simply based off of genetics, okay? However, if we increase the amount of UV light that we are exposed to, something fun happens. What happens if you go stand out in the sun for a couple hours or for a little while every day? What happens to your skin? Yep, you tan or you burn, okay? Well, you can do both, okay? But your skin gets exposed to more UV radiation, so as you get exposed to more UV radiation, you produce more melanin. Now, if you expose yourself to enough UV radiation in a period of time, you can burn, okay? That's when we get damage right now to the skin, okay? That's going to be something that's a little different, okay? But the whole idea here is that the melanin is supposed to stop that from happening. But guess what? I don't care if you have sat in a tanning bed for 30 minutes a day for 30 years. and your skin is as dark as that table, you can still get a sunburn.
You can still get cancer.
And you can still get cancer. It does not matter how dark your skin is. You can still get a sunburn. I don't care how good your base tan is. I've had this conversation with people like, oh no, I have a good base tan. Like it's fine. I don't need to put on sunscreen. Bullshit. We're going to be outside for like 3 hours, man. And it is sunny as hell. Okay. You can still get a sunburn and you can still get skin cancer. Now, one of the other issues that happens if you do have some of that dark skin, whether it's from tanning for a long time or that you just have darker skin in general, like say you produce a lot of those eumelanins and you just have really dark brown skin or really even like dark black skin, okay? That dark skin, you can't see as well when something goes wrong. Okay, I have like a bunch of moles and stuff right here that each and every one of them is on a picture in my dermatologist's office. Why? Because we know that at some point one of them is going to go bad. Okay, and we can monitor those situations by, well, monitoring them and understanding how big they are to begin with. But also, if something changes, we can say, oh, okay, nope, that one's changing, which means now we have a problem, and we can go scoop that bit out and hey, everything's fine. Okay, but if your skin is dark, you can't see those changes as well, and all of a sudden when you may not notice the skin cancer early enough, and it could have actually had a chance to get deeper and cause a bigger issue, or gotten really, really deep and gotten into your blood and then gone somewhere else and done something different, which can be really, really problematic. Okay, so now people with lighter skin like me, we are way more subject to getting skin cancers. Okay, however, because I have light skin, it's also a lot easier for me to notice those problems. So I'm less likely to get ones that are going to kill me than someone that might have darker skin, which may not notice those problems as early as I could. Because I can tell you, if one of these like freckles right here like turns black and triples in size, I'll know. That's not the case if my skin were darker. So that's something we have to kind of keep in mind. Just because you have dark skin does not mean you are immune to skin cancer. It'd be great, be really nice, but that's simply not the case. Now, it does help because the reason we're putting it around the nucleus is so that we can prevent the UV radiation from making changes to our nucleus. But that doesn't necessarily stop it altogether. It just decreases the likelihood. So instead of getting cancer at the age of 15, we might get cancer at the age of 40 instead, or later, depending on how lucky we are or how bad our burns were. I've had some pretty bad ones. The backs of my calves one day, like I'm a religious sunscreen user. Like if I know I'm going to be outside for more than 45 minutes, even if the UV levels aren't particularly high, I still apply sunscreen. And I have to use fairly big like high level sunscreen. Like I'm talking SPF 70 plus is what I'm usually using. Like to me, if it's lower than SPF 70, it's basically water and is useless. Okay. I have burned through SPF 70 and I've burned through it. Okay. But so like I have to use fairly good stuff most of the time. But I went fishing one day and I had applied it everywhere that I could, but I applied it while I was sitting down. I forgot to get my calves. I got below my calves, but I did not get my actual calves. And we were fishing and the sun was behind us most of the time that we were fishing and I didn't notice it. So I couldn't see it. My calves were purple when I went home. They weren't red, they were purple. It was bad. I couldn't sleep. It hurt so bad. Like it was horrendous. And then they peeled for multiple days. And like my doctor said that it actively scarred the skin on my legs. Like you are going to have skin cancer on your legs now. So like that's something you just have to be aware of. Like we'll just have to watch it. So instead of just watching your face and your back and your shoulders and your neck like we do on other people, we'll have to watch your thighs as well. Great. Yay. Thanks. It's like good to know. But that's from our melanocytes. Now, we also have our tactile cells here. This is a tactile cell, so that means it's going to sense touch. That's what the word tactile means, touch. Okay, so this cell is going to sense light touch. Light touch because it is up here in the epidermis, which means it is very, very easy to make the cell change shape, which means very easy to make it send its signal. That is in our basal layer. Now, as we move up from the basal layer, we're going to get into our stratum spinosum. This is going to be anywhere from 5 to say 10 layers thick. these cells are also almost all going to be keratinocytes. That's to say they are making and storing and producing the protein keratin. You'll notice that we have gone away from our cuboidal cells, which we kind of had down here, to now we're getting more into those just kind of amorphous squamous cells, okay? Now, the only other cell that we need to worry about in our stratum spinosum is going to be this little yellow guy right here. These are called dendritic cells, okay? If you ever see a cell that's got these like little feeler regions, so say we have a cell body right here, but it's got these little feeler regions reaching around out here, like just kind of reaching all around the cell, like looking for signals. These are almost always going to be called dendrites, okay? These are basically just kind of little feelers looking for stuff. In the case of our dendritic cells, these are looking for potential pathogens, looking for viruses, looking for bacteria, looking for fungi, looking for anything it can recognize as being a potential pathogen, at which point we can destroy it, hopefully, okay? Now, as we move away, so as these cells in the stratum basal divide, they're going to push their daughter cells out into the stratum spinosum. So this cell divides, is going to push one daughter cell up here, and the other one is going to stay in this place. That way we're always having something stay in the basal layer, but then we're constantly producing more cells out here into the stratum spinosum. Well, as this cell divides again, well, that means the cell that was the old daughter cell just gets moved up a layer. And then when that bottom one divides again, this one moves up another layer, right? And eventually it just gets pushed further and further and further away from the stratum basal. But remember that our blood supply is here in the dermis, which means we are getting further and further and further away from the dermis, which means as we get up here, our cells are going to start running out of nutrients. Eventually, we are going to get far enough away from our blood supply that we're going to start running low on some nutrients. When this happens, these cells are going to start to break down. As they start to break down, their nuclei are going to dissolve. Their organelles are going to break down. As this happens, instead of our nuclei being these nice little kind of complete structures like we have here, instead they're going to do this. They're going to become a bunch of dots, or what we're going to call, from now on, we're going to call dots inside cells granules. Okay? And the same thing is going to happen to our mitochondria. It'll become some granules. Our endoplasmic reticulums will become some granules. So these cells are just going to fill with granules as these things are broken down, okay, as they're breaking down into parts and pieces. So this layer is composed of a whole bunch of cells. So stratum is layer. It's composed of a whole bunch of cells filled with granules. So we're going to call this the stratum granulosum because it's a layer of a bunch of cells containing granules. That basically says, hey, we are still alive, we're still doing stuff, but we're starting to break things down, okay? We don't need these structures anymore. We're getting too far away from our nutrients. So we're going to start breaking these things down and basically just kind of nuke everything inside the cell with the exception of keratin. Now, our next layer is only going to be found in thick skin. Where did I say you could find thick skin?
Your palms and then bottom of your feet.
Exactly. The palms of your hands, your fingertips, and the bottoms of your feet, okay? So anterior surface of your hands, bottoms of your feet. That is our thick skin. Thick skin because it's going to be exposed to a lot more friction, okay? Now, because it is exposed to a lot more friction, so say like I'm holding on to one of those bars for a few minutes like I do every day, okay? Well, I am subjecting particular regions of my hand to lots and lots and lots of friction. So what is going to happen on my hand? What am I going to form? Calluses. There's a callus right here that's really, really obvious because it's on my middle finger, which means it's my strongest finger, which means that's probably where I'm putting the most pressure on the bar because that's where I can generate the most pressure, right? I have a nice big callus right there. There's also one there. Okay, but that callus is clear. It's clear because it's filled with this protein called eledin. The stratum lucidum is a whole bunch of cells that are filled not with keratin, but with a protein called eledin. E-L-E-I-D-E-N. Okay? That eledin is clear. And this is going to be found in all of our thick skin. So looking at my palms, it's here, it's here, it's here, it's everywhere. However, in these regions of lots and lots and lots of pressure, lots and lots and lots of friction, I make that layer especially thick, and I have formed a callus. So everybody see this kind of big, thick, clear layer right here on this real micrograph? That is a callus right there. And you can even see like the friction line. Like you can even see like the pressure line that's generated right here from that big division. So this is all stratum lucidum. This is a region of stratum lucidum that's really thick because we have a callus. And that's going to happen, like I said, anytime you are subjecting a particular region of your hand or your foot with lots and lots of friction, whether it's your shoe doesn't fit right, so that one toe slides, or the back of your foot slides in the back of your shoe a little bit, so it'll form that kind of region, or lifting weights or whatever that may be. Now, above the stratum lucidum, which once again, stratum lucidum not found in any place of our skin. I don't care how much friction you place on your forearm, it is not going to form a callus. Okay, it just simply can't. It doesn't have that skin layer. Above the stratum lucidum, though, we have the stratum corneum. Okay, the stratum corneum is the outermost layer of our skin, and it's going to be composed of dead keratinocytes. These keratinocytes are going to be adhered to one another. So we've gotten rid of all the stuff on the insides of the cells except for keratin and except for all of these cell adhesion proteins, which are going to allow one cell to stick really, really, really well to the cells beside it. This way we have this nice, really good connection between all these cells with one another. That way this area gets very, very, very strong. This is like if you put 15 or 20 layers of shingles on top of your house. Do you think any water at all is going to be able to make their way through that? Probably not. Okay, it makes it very, 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 very difficult for anything to get through it, just simply because the distance is just too great. It is too hard to pass through all of these things. That is where we get our protection from friction, protection from abrasion, protection from bacteria, protection from whatever. We have made a wall using these dead keratinocytes. So here's the difference between our thick skin and our thin skin. Notice that we see this little thin layer of stratum lucidum right here. So that is one identifier of thick skin. The other is the fact that we have 30 layers of skin right here versus like 10 over here. Okay, or right here. This is our stratum corneum on this side. So this is the equivalent of this over here. And these are at the same magnification. So that should show you how different those two things are. But once again, that's because this is the way we interact with the world. It's through the palms of our hands and the soles of our feet. Now, our skin color is also made not just up of melanin, which we talked about a little bit before, but is also composed of hemoglobin and keratin. Hemoglobin is red. This is what makes our red blood cells red. Okay. If you have a whole bunch of blood up close to the surface of your skin, so say you're going for a run and you're trying to cool off, so you put a bunch of extra blood out close to the surface of your skin is going to appear more red, just simply because there's more blood up close to the surface. So the presence of that hemoglobin and the presence of that blood is going to make it appear more red. Okay. If you have cells that do not have a whole lot of melanin in them, they're going to appear slightly pink just because they're going to be a little bit more transparent. So more of the red color of the blood underneath is going to be able to show through as well. That's why people with really, really pale skin will oftentimes look a little bit more pink than someone that, say, has a little bit more pigment in their skin. But this is especially true whenever we flush. So whenever we route additional blood out close to the surface of the skin, so we vasodilate this up close to the surface of the skin, so we get more blood up close to the surface, you're going to see more of that red color shine through. And that red color is just simply going to be because of blood up close to the surface. Now, another one is keratin. So keratin is a protein pigment that's going to be found in some vegetables. It's particularly found in things like tomatoes and carrots, thus carotene. Okay, it's like it says, yellowish orange. It's also fat soluble. That's why you really only see keratin like that reddish orange color in like a layer of fat. That if you have ever made pasta sauce, that layer of olive oil that will sit along the surface of it will contain a lot more of that orangey color than the rest of the pasta sauce will. It's simply because this is readily dissolvable into fat. Now, keratin is also was for a long time thought to increase our eyesight. The more keratin you had in your diet, the better eyesight you would have, was the idea. So Britain told all their pilots, or not even told them, force fed them lots and lots and lots and lots and lots of carrots throughout World War II. This is not a joke, actually. They basically made them eat 5 or 10 times a normal human being's amount of carrots. And they were doing this every day. They had to eat a massive number of carrots and stuff like that. And it was like, it's because we want them to have as good an eyesight as they possibly can. I mean, they're flying at night. They're trying to keep the Germans away. All these kinds of things. We need them to be able to see. So like, hey, let's give them more carotene so they can see better. So much so that a bunch of that pigment got stored in their skin. So it made their skin more orange. Not quite Oompa Loompa orange, but also not Oompa Loompa orange. Like noticeably orange in color, simply because of how much carrot they were being forced to eat. Here's the best part. Once you reach the actual adequate amount of carotene in your diet, it doesn't actually do anything to increase your eyesight. All it does is make sure that it doesn't get worse. So like a carrot a day would have been more than enough to make all of these poor pilots see just as well as they could have at the start of everything. But instead they were having to eat way more than that. So their skin turned orange, but it did nothing to help their eyesight. And I was actually told by someone in the first class this morning that apparently this has become a thing on TikTok now, like where some of the people on there, like in their skincare stuff, is actually telling people to eat more carrots so that their skin looks more tan. Because they're, yeah, it's not a joke. I was actually told this by students. Like, that's hilarious. Would actually work. It would make your skin look more orange. And I guess there is a link between orange and tan. But yeah, fun stuff. Generally, I don't recommend getting your advice from places like TikTok. But who am I, other than just an old fuddy-duddy? So here we have our melanocyte zoomed in a little bit so you can see it. We can see these little, where's my arrow? There it is. We can see these little feeler regions kind of reaching out here so that we can pass those melanin granules into our outlying cells. And then we can see those melanin granules lining up around the nuclei of those cells, protecting them from our sunlight. Now, we've already talked about fingerprints and stuff like that. Moles are basically just an area where we have an overgrowth of these melanocytes. So if we were to look at the stratum basal in an area where you have a mole, you see a much higher proportion of melanocytes in those areas than you would in a place that does not have a mole. Okay, basically you're producing a lot more melanocytes and thus a lot more melanin in those places. So you have these like localized dark spots. The same thing goes for freckles, but freckles, instead of producing some of the eumelanin pigments, which are going to be that kind of brown to black range, instead these are going to be those kind of yellowish or brown spots. It's also fun to see people that are really freckly and have like really fair skin go get sunlight, because instead of tanning, they just get a lot more freckles. It's quite funny. But once again, these are just localized areas of melanocyte activity. Here are examples of the fingerprints on your skin and how you can see like, oh yeah, if I were to touch something with this, I could get that much more surface area that I can use to grab onto that thing, because these are basically like little ridges that as you put pressure on them, flatten out and give you more touch on the thing that you are grabbing. However, each of these is individual to us. So we get our little fingerprints, and we'll have our own little patterns on the bottoms of our hands and our feet. But it's also all really so that we can grab stuff a little bit more efficiently. Sunscreens are important. Wear sunscreen. Use it all the time, every day. You're going to be outside for more than 10 or 15 minutes or so. Use some sunscreen. Now, some UV radiation is good for you. In small doses, UV radiation is good for you. It helps you to make vitamin D, all those kinds of fun things. But that is not like 1 o'clock in the afternoon in East Texas in August is not the day to do that, because you can literally burn your skin in 10 minutes with the amount of UV radiation and stuff like that that we have here at that time of day. So you have to be careful when you're doing those kinds of things. So some amount of UV radiation is good, but large amounts of it are not. And our sunscreens are really, really, really good at absorbing all of these UV rays and keeping them from damaging us. So they are a great idea to do that. All right, now we get into the dermis. The dermis, we have two primary layers. We have the papillary layer and we have the reticular layer. The papillary layer, that's going to be these kind of finger-like regions right here. These are going to be filled with areolar connective tissue. So what's going to make up our papillary layer? So we get lots and lots of collagen, lots and lots of elastin. So our skin is both stretchy and strong. The ability of our epidermis and our dermis to stick together even though we're putting a bunch of force and stuff to them, is because of the strength of areolar connective tissue, and it's elastic to bounce back to shape, and it's collagen to keep you from being able to stretch it too far. That is why it is so difficult to separate these two things from one another, in addition to all of the surface area that we get holding our epidermis to our dermis in this papillary region. Now, you're going to find lots and lots of blood vessels running through here so that we can get plenty of nutrients up into the epidermis. You're also going to find lots of nerve endings. The nerve endings we find in the papillary region are going to be more sensitive to things like light, touch, things that are happening on the surface of the skin. But by putting them down in the papillary layer, we are protecting them from the worst of things. It's going to be really hard for us to hurt our nerve endings with something like, say, sunlight, because they're going to be found down here in our papillary layer versus what would happen to them if they were up here in the epidermis. Okay. Now, below that, we have the reticular layer. So the reticular layer is going to be composed of irregular connective tissue. Okay, so dense irregular connective tissue, which has bundles of collagen fibers all kind of running in one direction in each bundle. But one bundle may run this way, and another bundle may run this way, and another bundle may run over here and over here. So we get strength, but we get strength in lots of different directions. Whereas dense regular connective tissue, all of those fibers are running one direction, and that is the direction in which you get the strength. This way, because they're running everywhere, we get lots of strength in lots of different directions. So our dermis is actually going to be very strong no matter what direction that friction or pull is placed in. Okay. Now, we're also going to find lots of other structures found throughout here, whether it's our hairs, our sebaceous glands, oil glands, sweat glands, and stuff like that, as well as lots of other less sensitive nerve endings down here where we sense stretch or where we sense kind of vibration and stuff. Now, those collagen fibers are also generally going to run in one direction. They're going to be parallel to one another in particular regions. So like right here in this kind of upper abdominal region, so kind of just above your belly button here, so just above your umbilical region, we have these cleavage lines which are running this way, which means that's the predominant direction of the collagen fibers in the skin in those areas, which means they're going to be very, very strong in that direction. But say I get a cut in that direction. Well, there's also a tension in that strength of those collagen fibers in that particular direction. So if we slice it in that spot, well, what's going to happen is the strength in those fibers are going to pull that wound more open. It's going to be a lot harder to close that wound because that cut is not, or because that cut is being pulled against by those collagen fibers. So it's going to make those wounds kind of pucker up, okay? Make them hold themselves open more, which means to close these, it's going to take a little bit more effort because you have to close them with something with enough force to overcome the force that's being applied by those collagen fibers. So a cut like this, a vertical cut in this region right here, is going to require stitches or staples or something like that to make sure that it doesn't open back up, okay? Whereas a cut that is parallel to those cleavage lines, well, you're not actually affecting the overall pull of these things, and the pull of those lines is more likely to kind of elongate the cut, but it's actually not going to tear it any more open, okay? So these are going to be a lot easier to close. Like you could close a cut like the one we see right here with just a Band-Aid, even if it's as long as it's a fairly shallow cut, you could just close this with a Band-Aid. You don't have to worry about the skin itself trying to pucker itself back open, where it's going to keep it from kind of closing, okay? I have a cut that is perpendicular to this on my calf in basically the same spot. It happened right here, down into the fat. It got closed and held closed because it's perpendicular to the lines. It had to be held closed. So they held it closed with staples. So that was real fun. I then played baseball, literally the next day. It was covered with plastic and stuff. It was fun. The best part wasn't actually getting the staples, because that didn't hurt. The best part was getting the staples out. That was an interesting, they give you a pain shot, but it's still just like, that is an interesting experience. Like feeling the pull of these little pieces of metal that are this wide being yanked out of your skin. It's odd, very, very odd. But those lines of cleavage are important. Now, say you want to get a pigment to stay inside your skin. Well, we already talked about how the cells in our epidermis are constantly being replaced by cells from our stratum basal. Well, if you put dye or an ink in that particular area, it's not going to stick around. However, do we see the same linear progression of cells from our dermis? No, that's because this area down here is not particularly cellular at all. Most of the stuff happening down in this layer is just fibers that are found outside the cells because it's connective tissue, right? It's cells in a matrix. Most of the stuff that you see is in the matrix. It's not the cells themselves. Okay. So because of that, if you were to put ink down here, now it won't go anywhere. Okay. Because you're not replacing all of this stuff in a particular direction. It's just going to kind of hang out in that region. So you'll be able to see it. Now, over time, cells will divide, stuff will move around. So your tattoos and stuff may get a little less or a little bit fuzzy or a little bit less kind of sharp and crisp. That's why if you've ever seen someone with, like, if you know an old sailor or something like that, and you look at their anchor tattoo that's on their arm, okay, it's a lot less distinct around the edges than someone who's is brand new. And it's simply because, like, it's not that it's going away and getting replaced, it's still there. It's just there's other stuff now that's in between the bits of ink than there were when it was first put in. But it is still there, rather than if you just do it on the surface of your skin. Like, you could take a permanent marker, like, do I have a Sharpie? Here. Like, I have no problem doing this because I know this will go away. I could leave it there all day, not shower, leave it there for a few days, but over the course of a couple of days, it's just going to go away on its own as these cells just get sloughed off. It's fine. Yeah, I colored the cells, but it's not that big of a deal. Okay, that is not the case with something like a tattoo because it's put into the dermis. However, if it's not down in the dermis, it will not go away. Or if they don't get the needles deep enough, rather, and they accidentally put it in the dermis, it will go away, at which point you get to be really mad at your tattoo artist. That's also part of why it's actually really difficult to get tattoos in places like, say, the palms of your hands or the soles of your feet, is because that skin is that much thicker. So in order to get down to the dermis, they have to use much, much longer needles to get that ink far enough down. They're far more likely to inject that ink just into the epidermis, and that stuff would go away. All right, so we have secretion, absorption. Or sorry, we have protection from the external environment. We have water loss and gain. Vitamin D synthesis is something we mentioned but didn't really talk too much about. Vitamin D synthesis is very important. Vitamin D is a precursor to a molecule called calcitriol. Calcitriol is going to make it where if we take in calcium in our food or phosphate in our food, we are going to be able to absorb that and then make use of it. If we do not have calcitriol, we can't make use of calcium from our diet. We can't pull the calcium out of the spinach that we eat or whatever, and then take it into our blood and then make use of it in our tissues. We don't have vitamin D3, we can't make use of that. But here's the fun bit. You need calcium in order for your bones to be alive, or in order for them to have their shape and structure. As we know, they're made out of calcium. That's important. However, without calcium, your nerves can't send a signal from one to the next. Like, it sends the signal down the length of the nerve using sodium and potassium. But actually going from one nerve to the next, spanning that gap from one nerve to the next, requires calcium. Calcium is going to be in the synaptic ends of our nerves. So for one nerve to talk to another nerve requires calcium. In order for your muscles to contract, requires calcium. Calcium is very, very important. If we can't get calcium from our foods, our bones are going to get soft and our bones will break. And our nerves and our muscles will not function correctly. Both of those are bad. To the point where when people started spending a whole lot more of their time inside, they start getting a lot less UV radiation, which means they started producing way less vitamin D. And people's bones started getting soft because they weren't producing enough vitamin D to keep their bones strong. So FDA, or not FDA, it was one of those groups. Like, okay, let's go ahead and start supplementing people's diets with vitamin D. So they started adding or supplementing vitamin D into people's food, particularly one food item. Anyone know the major food item that started getting vitamin D injections or vitamin D supplementation to it? No, that came later. I've seen it in two. Milk. What is the predominant nutrient that you're trying to get out of milk other than fat and sugar, which are both important and are in large concentrations in milk? That's part of what makes milk good. What's the other main thing that you're getting? You get like half of what you need over the course of a day in a single cup of milk. Calcium. That's real damn convenient. So instead of putting a supplement into something else that you're not going to be getting calcium out of in the first place, let's go ahead and put the vitamin D supplementation in the thing that's giving you your calcium. So that's what they did. They added vitamin D supplements to milk. Get to the 2000s, people stopped drinking as much milk because they realized, there's a lot of fat and a lot of sugar in this, and it's more fat and sugar than a lot of us need. So people stop drinking as much milk and they start drinking more juice. So what do they start doing? They start adding calcium and vitamin D into those things. So that's why you can find orange juices and cranberry juices and stuff like that that have calcium and vitamin D added to it. A good place to get calcium in your diet is in places like spinach, also places like milk and stuff like that, particularly in milk. But it's also really, really high in like your dark green vegetables, like your spinaches, your broccoli and stuff like that. However, you can't really get it from your food. The only way you get it is actually from your skin. UV radiation hits your skin. When that UV radiation hits your skin, we produce vitamin D3. We then take that vitamin D3 and in your blood and in your other systems, we turn it into calcitriol, at which point we now have calcitriol in our blood. We can't make our own vitamin D without getting exposed to some amount of UV radiation. So some amount of UV radiation every day is good. However, there's such a thing as too much. All right. Our skin is also responsible for absorption of some things. Many things can actually cross that barrier. But we also need to protect ourselves from the outside environment as far as immune cells. Like, so say something does get into our epidermis, once it makes its way down into that stratum spinosum layer, we will have dendritic cells which can fight against it. We also know temperature regulation is very, very, very important. We sweat, right? When it's hot outside, you sweat, your skin flushes, you put a bunch of, like when your body temperature gets hot, you put a bunch of extra blood out close to the surface of your skin so that the outside environment can soak up some of that heat. You also sweat so that you can then take water out of your body and put it on the surface of your skin and start to cool that via evaporation. So if we vasodilate, we can release heat because we basically put more blood up close to the surface of the skin so we can have the outside environment hopefully take up some of that heat. Or we can vasoconstrict, like when it's cool. Like in here, it's fairly cool. If you vasodilated right now, vasodilated right now, you'd put a bunch of blood up next to the surface of your skin where it's cold. So you would actually cool your body. That's fine if that's what you need to do. But if your body is currently cold, that means we need to conserve heat. So if we want to conserve heat, we actually constrict how much blood is actually going close to the surface of our skin. So our skin is going to get more pale. Okay. That's also why when someone has a fever, you'll notice that their skin is usually kind of pale and clammy. Their skin is kind of cold. Like the surface of their skin feels cold and their skin looks real pale. That is because their body is trying to conserve as much of that heat as they can so that they can utilize the heat in their body to fight off whatever it is hurting them. So they're going to try and hold on to that extra temperature that they have. So they're going to try and lose less of it to the outside environment. Now, if you touch them and you actually put some pressure up against those blood vessels, that's when you'll notice they're nice and hot. But if you're just touching the outside surface of their skin, it'll actually be fairly cool. Then we, of course, have sensory reception and stuff like that. Now, it's time to look at some accessory structures. This is where we get our nails. Fingernails. You may not think that these are important, but watch. I can take my hand and I'm not bleeding. That's nice. The bones of your fingers are very, very pokey. Don't believe me? There's a real skeleton in the back of the room back there, and you can see its hands, and you can see how pokey the ends of those bones are. I was hitting this with enough force to have forced a really sharp object through my skin. It did not pass through my skin, though, because it hit my fingernails first. Okay? The fingernails are going to protect the ends of the bones of your fingers, okay? Because they basically are allowing that force to stop. Also, when I grab this object right here, you'll notice that my fingertips are changing colors. Out there towards the edge of my fingernails, you'll notice that it's turning white. Why? Because I'm grabbing this with enough force to push all of that blood out from underneath my fingernail. Okay? It gives you something to press against. Instead of pressing against the bone, instead you are pressing that skin against the fingernail and all of that surface area of your fingernail, so you have this nice stuff to press against. So it's going to help increase the amount of force that you can apply through the ends of your fingers without damaging bones or soft tissues. Okay. Now, we do not use them for like gouging out the eyes of our prey or anything like that, like you would if you're a cat or something like that with big talons. However, our fingernails are still important. We also get lots and lots of surface area. Part of the reason we get that strength that our fingernails don't move like when we're hitting stuff is because of how wide our nails are. Okay. That width gives us a lot of surface area so that it doesn't move or slide. Like it's really difficult to dislodge your fingernail from the nail bed because of the amount of surface area that we have. We also increase that surface area a little bit by passing underneath our skin a little bit. The actual nail matrix starts way back here. So our nails have a root where we go underneath the cuticle of our nail. Okay. Now we also have this kind of half moon shaped region right here, this little white spot. It's called the lunula. I actually saw this as a trivia question the other day on a show I was watching. I was like, hey, I know the answer to this. I have very esoteric knowledge about some things. This is one of those. I'm not going to ask you that because that's a dumb thing to know. I just happen to have known it. But our nails do have lots and lots of surface area because of this big nail bed right here and the connection between those. Now, if something happens to your nails, it can take a very long time for that injury to heal itself. Our nails take a very long time to grow, and they grow only from right here. So if you hurt something right here, you have to wait for all of these cells back here to push that thing all the way out before it goes away. For instance, I have an injury on my long toe on my right foot because my daughter dropped a chair on it. Okay. Or made me drop a chair on it, I guess is what happened. Landed, completely broke the nail. Tore off from that particular spot. And it had this nice big gouge where it like went down and kind of tried to grow into my foot a little bit. That was 14 months ago, and I still have about yay far to go before my nail is completely grown back. And I have relatively fast growing nails. Like I actually keep my nails fairly long just because they grow fast. Like I cut them back, I cut them all the way back, and like I felt like I did this like a week or two ago, and they're already here. Okay, my nails grow pretty fast, and it still hasn't repaired itself. Okay, now that also means that we can really, really monitor someone's overall health, and not just what their health is right now, but what their health has been over a fairly long period of time by looking at their nails. Okay, if their nails are particularly brittle or something like that, this could be because they have a underlying health problem. If someone has a vitamin deficiency or something like that, we can actually see this as a little bulge or a little kind of ridging in their nails, like where they grow in these like little spoon shapes. That tells us, hey, we have some sort of thing that's going on with this. And if that grows out and it stays in that spoon shape, well, that means they're maintaining that issue. If it just kind of is in just one little spot and it goes away, well, that means they kind of resolved it. Like, oh, they weren't getting enough vitamins in their diet for a little while, but then they continue getting their vitamins back in and everything was fine. Or they had a fungal infection, but they had their fungal infection 6 months ago based off of where that little divot in their fingernails are, and so on and so on and so on. It's kind of fun. We also have hair. Hair is very, very, very important. The main thing that our hairs are going to do, the main thing our hair is going to do is basically act as a sensory receptor for us. So the primary thing that our hair is doing is acting as a sensory receptor, at least on most of our body. Okay. That's because connected to our hairs, we're going to have a very sensitive nerve. Every time one of our hairs moves, it sends the signal, hey, something is touching me. And these are, once again, very, very sensitive. Now, our hair connects to our skin and down here in this area that we call the hair bulb. So the brown bit right here is the actual hair. The dark brown bit that you see in the center of the hair is going to be called the medulla. Outside of that, we have the cortex, and then we have the outermost layer that we're going to call the cuticle. Okay. These are basically still going to be like the same cell that you have in your nails or even in your skin. So they're basically going to be these little scale-shaped structures. Okay. Because these are little scale-shaped structures, we want to hold them all together. We hold them all together with oil. The oil that we're going to use to hold our hairs together, or those little scales together, is going to come from our sebaceous glands, which we're going to find right next to our hair follicles. So this gland is a sebaceous gland. It secretes an oily substance called sebum onto the surface of the hair, follows the hair up, at which point it stays connected to the hair, and then some of it will also get out here onto the surface of our skin. But it is oil. Well, one of the things that we needed to protect against was water. Well, does water mix with oil? No. So if we put a real fine layer of oil on the surface of our skin, what have we just done? We've prevented water from being able to make its way in, simply because we have a little bit of oil on the surface of our skin. Now, what we're also doing with that sebaceous fluid is we are taking those little skin, those cells, and we're helping hold them together, okay? As long as we keep our skin moist with that oil, we can help the cells stay tightly packed together and stay nice and smooth. The same thing goes with our hair, okay? If you've ever noticed, like if you don't wash your hair or whatever for a few days, your hair will get just a little bit oily, but it will also hold itself together like in clumps better. Okay, like when your hair gets oily, you'll even notice it'll be kind of clumpy and sticky. Okay, but it's also nice and smooth. I do not wash my hair more than say once a month. Okay, I just rinse it. Okay, it's fine. Ron Swanson said, "Be like a bear," and I'm basically acting like a bear. It'll be okay. Okay, or if it's good enough for a bear, it's good enough for me, I think was the exact quote. But water's fine. My hair is not particularly oily right now. I have not washed it in, I don't know, probably a week and a half. Something like that. Not particularly oily. There's enough oil there that it all holds together. When I wash my hair, you'll know, because my hair is going to come in here and look like this. It's just going to be a puff ball. It's going to be all frizzy. Why? Because I don't have the oil holding the little scales of my hair together. So they just trap air and trap everything and just like turn into this little fluffy fuzz. Okay. That's why your hair gets that way after you wash it with something like shampoo. And that's simply because you're washing off all of that oil. You're also washing off all of the oil off of your skin whenever you wash your skin with soap. So your skin gets dry because you've washed off all the oil. Also, because the cells aren't being held together by the oil anymore, your skin gets a little bit kind of pale and kind of whitish looking, kind of scaly or ashy. Why? Because you don't have the oil that's holding them together. So we add it back in by putting on lotion or whatever that may be, so that we can try and replicate what the sebaceous fluid is normally doing for us. Importantly, we don't have that in our hands. Our hands just have sweat glands. We don't have hairs for those. Okay. Now, also associated with our hairs are these little muscles. This is called the erector pili muscle. Erector tells us that it's going to take this hair and stand it up when that muscle shortens. So when does that happen? When might your hair stand up on end? When you get goosebumps. That's exactly what happens when you get goosebumps. You get goosebumps because you are standing your hairs up on their end. But when do you get goosebumps? When you get cold. When you're scared and when you get cold. Those are both right. Okay, those are when you stand your hairs up on end. Okay, you do it for very different reasons in those two environments. The first time we'll talk about, say, is cold, because we're getting into the time of year where it's a little chilly in the morning this time. If you walked outside this morning and you looked at one of the birds sitting on a power line or in a tree or something like that, they looked very different than they did at 3 o'clock the day before. 3 o'clock, they were skinny. 6 o'clock this morning, they were little fluff balls. Why? Because they had goosebumps. They fluffed up whenever they got their goosebumps. Goosebumps make our hair stand up on their end so that we can trap air underneath the hair. So we would have hair here, a layer of air, and then we would have our skin. That little layer of air, we then warm up using our body heat. So we basically put on a jacket. That is what birds and dogs and cats and stuff like that do whenever it gets cold. They fluff up their fur and they trap a layer of air underneath their fur or underneath their feathers, and then they stay warmer that way. they're going to lose less heat to the outside environment because they're trapping that air by standing their feathers and stuff up. So they look fluffy. Your dog goes outside, shakes, and turns into a little fluff ball because they're putting on a jacket. That's literally what they're doing. Okay. However, I can see through my hair. I can literally read this slide through my hair on my arms right now. Do you think I can trap any air at all with my hair? No. I walked outside right now, I'd still get goosebumps though. Why? Muscles getting shorter. Change in temperature says, hey, you should put on a jacket. So you can get goosebumps, but it's not actually doing anything. Not actually trapping air. So why does it happen? Because I'm a mammal, and all mammals get goosebumps when it gets cold. Regardless of if I have the hair or not, I'm still going to have the same thing happen. This is a vestigial trait. It happens because I am the thing that my common ancestors were. Your dog has fur. Your dog is a mammal. You have fur. He just has more than you. So his actually does stuff. Yours doesn't. We're still mammals, so I still have this trait. Guess what? You have a tail too. It's tiny. It stays inside your skin. But you still have it. Vestigial trait. Doesn't do anything. Also doesn't cost us anything. Fun.
So do the naked cats get?
They get goosebumps too. Yeah. Uh-huh. They have hair. You just can't see it. They still have the hair follicles. So they have, like, if you were to look at them, like they would be, some of their hairs might be like this part right here may be so thin that it's invisible, but this part will still be there. So yes, they'll still get goosebumps. Now, when you're scared, particularly, you're going to get goosebumps right on the back of your neck for the same reason that your dog and stuff do too. Your dog does that like when they get mad, but they do that as a signal to the other stuff that says, hey, it is like, if the situation is fight or flight, I'm ready for the first one of those options. And if there's a signal to the other things that they're interacting with, like, hey, I am ready to fight if you are. Okay, that's why they get those hackles and try and like prevent that. Okay, as a signal. You have it for the same reason. It's just you don't have enough hair back there for the person that you're looking at to understand, like, oh, they have actually had a visceral response to this situation. But you still do it for the same reason. And it's once again basically just a vestigial trait. So goosebumps are completely vestigial. Now, hair does prevent heat loss, particularly on our head. Don't believe me? Go shave your head. It will get cold now. Okay? And y'all have at least long enough hair that you understand, like, if you put your hair up in a ponytail, get it off your neck, all of a sudden your neck gets much, much cooler. So like when it's hot outside, most people like to wear their hair up so that their neck and stuff is a lot cooler, right? So it definitely prevents hair loss, or not hair loss, heat loss, whenever we have it in high enough concentrations like we do on our head. Also on our head, it's going to do a good job of protecting us from UV radiation and stuff like that, so that we don't get sunburns and stuff like that on the top of our head. Now, if you wear your hair in a part, you are actually still going to be exposing that region of your hair a little bit, your head a little bit, and sometimes people will still burn along that line. So they actually make special sunscreens just for dabbing onto that particular area so that you don't have that happen.
That's static electricity.
Oh, that, wait, what? Oh no, that's just static electricity. That basically just it simply starts interacting between our hairs and stuff. It bounces back and forth. That's why they all kind of interact with one another. But that has nothing to do with the structure of the hairs themselves. Mm-hmm. Yeah, it's here, but not necessarily related. All right, I think we talked about those. All right, now we do have sweat glands and sebaceous glands. Sweat glands, we have two different types. We have apocrine and merocrine. These are both going to be different types of sweat glands. These are both going to put their sweat onto the surface of the skin via a sweat gland duct and then finally through a sweat pore. Okay. Now, eccrine sweat glands or American sweat glands, these are the most common sweat glands. These are going to be found basically in all of our skin. And these are what are going to secrete normal sweat. This is basically going to be 99% water and then 1% a bunch of other stuff. This is going to be every now and then a little bit of waste, maybe some metabolites, but usually this is just going to be in the form of electrolytes. Our primary electrolyte in this case is going to be our salts, and really primarily sodium. Where water goes, sodium will go. Okay. And vice versa. If you need to put water somewhere, you give it some sodium and water will go there. Okay. That's also why it's bad for a lot of people with high blood pressure and stuff to have really high concentrations of salt in their diet, because that's going to make them hold on to extra water. When you hold on to extra water, that's going to increase your blood pressure. So if you have a lower sodium diet, you will have less water in the system and thus less pressure in the system. Okay. So that's one of the reasons why having a lower sodium diet can actually lead to less blood pressure, simply because you're holding on to less water. But sodium is going to be the primary ingredient in our sweat other than water. Now, every now and then you will find particular waste products. A good one of these is like MSG. So monosodium glutamate is a chemical that we cannot metabolize. So whenever we take it in our diet, we tend to try and get rid of it as much as we can. The main place that we will get rid of it is through our sweat, or one of the places that we'll get rid of it is through our sweat. So if you eat a meal that's really, really high in MSG, you'll find that you kind of sweat out that food a little bit over the next few hours as it's trying to go away. If you've ever had the meat sweats, like after having barbecue or a steak or something like that, that's literally what's happening, is you're getting that smell of meat and stuff out of you because you're literally sweating out the MSG. Pigs can't sweat though. So because they can't, they have to do something with the MSG. So they store it in their belly fat. So pigs have a really high concentration of MSG in their belly fat, which we then cut out, cure, which makes it have more MSG. And then we slice it up and fry it into bacon. You wonder why bacon tastes great? It's because it's a natural source of massive amounts of MSG. It's like putting bacon in something is basically the same thing as taking a shaker of MSG like they have in like Southeast Asia and stuff like that and doing this to your food. That's why it tastes good though, because MSG is awesome. May not be good for you because you can't do anything with it. But man, it tastes great. It makes other food taste good too. But we will do that with some stuff, but primarily we're moving sodium out. But its main job is thermoregulation. Why? Because we're putting liquid on the surface of our skin, which then absorbs all the heat from the surface of our skin and evaporates, and we get evaporative cooling and we cool off. Apical sweat gland is a little different. These are a little bit more heavily coiled. We're going to find these really in our axillary regions, so in our armpits and in our pubic and anal regions. These are going to produce a different type of excretion though. This one's going to contain proteins and lipids. When that happens, you're now producing something that things can eat, which means over time, when those bacteria and stuff are eating it, those bacteria are replicating and they're producing their own poop, which is going to produce odor as a byproduct. Okay. So that is why you tend to get this, especially once someone has hit puberty. That's when you start to produce more of these apical, like actual apical sweat, which contains those proteins and lipids, so bacteria and stuff can live on it. Okay. That's when you get the kind of smelly sweat and stuff like that, versus like a small child can run around all day and really not stink from it. The difference is because our apical sweat glands start to be more active during puberty. Sebaceous glands are where we're going to make sebum. This stuff is fun. It is a very stinky substance, but it's a lubricant for our skin and hair. It kills bad bacteria on the surface of the skin. Not good bacteria. We actually have good bacteria, like resident bacteria on our skin that eat sebum just fine. But bad bacteria, it doesn't like it. Or many bacteria don't like it. So it does kill some of them. And it discharges directly onto the hair follicle. This is part of what keeps our hairs nice and smooth and stuff like that. Now, there are other glands in our integumentary system, but these are by and large very, very small. Our ceruminous glands in our ears, and then mammary glands. We'll talk more about those in the reproductive system. But here we have a American sweat gland, and then we have an eccrine sweat gland right here. Sorry, apical sweat gland here. So eccrine is here, and then apical here. This figure basically just shows you how wound healing and stuff works, but this is more physiology related than just anatomy stuff. All right, so now what I would recommend doing is spend a little bit of time looking at the models on the table, see if you can find the various structures that we talked about, see if you can identify the various layers of the epidermis, see if you can identify the dermis and the layers of the dermis, see if you can identify the particular structures within those things? And if so, we are good. If you're wondering which structures you need to know, that is what is in the list in the outline for the chapter. Fairly straightforward. As you noticed, we got a little bit deeper into some stuff today than we have been able to do recently. We're going to do a lot more of that. We're going to be a lot deeper into particular items now than we were in the past. However, a lot of people find that a little easier still. It's still like we're not covering an entire course of information at one point, so which is nice. Everybody good? All right, let's get to it then.